My name's Associate Professor Ben Holken, and I'm a member of the School of Mechanical and Mechatronic Engineering here at UTS in the Faculty of Engineering and IT, and I'm downstairs in our incredibly well-equipped Dynamics and Mechanics of Solids laboratory. And what I have with me here in front of me today is an experimental scenario which represents an 8 degree of freedom system. We have an 8-story tower here to my left with 8 lumped masses evenly distributed along the length of this hollow rectangular cross-section beam, which is clamped at the base and free at the tip or the top. This tower has been instrumented with 2 MEMS variable capacitance DC response accelerometers, arbitrarily chosen to be mounted on level 7 and level 1. I have them on that side of the tower because I'm going to use my instrumented modally tuned impact hammer to impulsively excite the structure at each of these various degrees of freedom in turn, and I will capture approximately 3 to 5 averages for each of these different towers and build an FRF set taking into account the response at each of these locations for excitations at the various degrees of freedom along the tower. I can then use that data set in software using my Simcenter Testlab modal analysis package, which is available to me here on this device or on the UTS workspace for candidates that have collected these data in the laboratory and wish to process them offline to do the modal analysis part of this experimental measurement campaign. We have the geometrical details and the material properties for this tower, so we can simultaneously undertake a simulation using, for example, SolidWorks simulation, and we can predict the natural frequencies and mode shapes of this kind of a structure and compare and contrast them with those that we can capture from experiments. This video will work through in a detailed way how to set up the acquisition system, how to validate this channel setup, how to build a geometry, how to collect the data sets. Here's a little bit of a close-up of the instrumentation that I'm using. This is the power supply for my 2 DC response accelerometers, which I have mounted to the tower and which are routed by cabling over here. They are then connected from the outputs from the power supply into these 2 channels, 2 and 3, on the data acquisition system. On channel 1, I have my instrumented impact hammer with a nominal sensitivity 2 millivolts per Newton, which I've also defined in software. This device is IEPE, ICP, so if I remove the cable, it recognises there's no sensor attached, goes short circuit, I get a red light. When I reconnect it, I get a green light. These 2 channels have been conditioned externally. These green indicators don't tell me whether or not I'm closed circuit or not, they're just expecting a voltage. So there is a little bit of capability, intelligence built into the acquisition system, particularly with integrated electronics, piezoelectric. You can see they've got the connector here to the laptop, the power supply, the battery sits behind here. This is powered on currently. There's a communication module above. Here's my laptop with Siemens Simcenter installed on it. And this device here is an electrodynamic shaker. If I was to do a shaker measurement campaign, instead of my impact hammer, I would use a shaker such as this with a stinger mounted to the structure to excite the structure. In that case, I would provide an input signal from the output here on my communication module into the input of the amplifier and very carefully use that to excite the structure instead of the modal impact hammer. So having explained the hardware and the experimental setup that we have in the laboratory, I'm now going to explain what to do in software. Here is the shortcut for the Testlab, Simcenter Testlab suite of products, and we're doing today a structures acquisition analysis. So we go into structures acquisition folder, and from there we take the impact testing workbook. As you will see in the other cutaway, when we launched the software application, the laptop and the data acquisition front end are now busily negotiating for a connection with one another such that we can begin the process of defining the test campaign. And here you can see my file menu, which looks like any other kind of Windows-based application. So the first thing I'll do is choose to open a new project. This will continue to negotiate the connection between the front end. It's activating the various channels that are in the default project setup. So we have to wait a few seconds for it to build a new project for me. I've previously used impact testing on my profile, so some of the configuration changes that I've made previously have been retained. If you're using this for the first time, there may be some differences with what you see here, in particular this geometry workbook, which I've added in down here and is available from the Tools Add-ins option up here. Here you can see there's a number of add-ins, in fact, that I've included already, geometry, and because I'm doing a modal acquisition campaign, I've already added in the modal analysis to be able to subsequently do that processing of the FRF set to determine the mode shapes and resonant frequencies. I can, once I've added in my additional workbooks, I can change the workbook configuration to make the workflow more logical. So I know, because I've done this before, that it makes sense for me to have the geometry workbook here before the channel setup. The default would be for new add-ins to be added at the end of this list, but I can move them around to suit the way I prefer to operate. As you can see, I've moved the geometry workbook here to after the impact setup. That doesn't make sense from a workflow standpoint. I'll move it back here to before the channel setup, and you'll see why when I go ahead and move forwards through this workflow. These are the major workbooks here that we see along this axis here. Here are some of the minor workbooks. For each of these major workbooks, there's a minor workbook which will change from one workbook to the next. Having a look at the navigator, this looks a little bit like Windows Explorer. So this is my new project, which has not yet been saved. So it's just called Project 1. And within there, I have Section 1. Of course, I can save this project, give it a name. Some other people have been working on here before, so I can call it 8-story tower impact. And I might like to give it a date, just so that I know which version it is. And I'm going to change my project, my setting to setup. No, I'm not. I'm going to rename it to setup. Okay. So that's the navigator. As I create data, make measurements, create geometries, for example, this folder here will be populated with information. I'm doing a modal analysis, a modal acquisition campaign on a tower. So I'm going to go into the geometry workbook and define a new component called tower. I can accept the table, and now I need to go to the node setup. These nodes are going to be named accordingly from the bottom 1, 2, 3, 4, 5, and 6. Those are my 8 towers. I know, because I've made measurements of it, that the separation of these towers is 25 centimeters. So that will be 0.25, 0.5, and so on, all the way to, of course, 2. But it's your responsibility as the engineer to determine the geometry and define it accordingly. Once I accept the table, you will see that in the bottom, I have a series, and I can change the view to left, right. I have a series of degrees of freedom, and I can choose to turn on the names of the degrees of freedom. It's very important that we make use properly of this naming convention. Since I've done that properly, I will save it. And I can then use this geometry ultimately to set up my channels, because I need to collect measurements that are properly associated with these degrees of freedom, such that when I come to animate the mode shapes, they are animated on the geometry that I've just created. I can't overemphasize how important that step is to get right. Otherwise, we might have to do a lot of renaming subsequently. What I would also like to do is have some connections between these points. So I will interactively join these points up by single clicking left button from 1 to 8, and then when I get to 8 I'll do a double click. That finishes the process. You can see that it builds this table here with the connections between the various degrees of freedom. Had I not done that properly, and it looks like there's a line missing there between 6 and 5 and 6, so we maybe need to manually edit that. I didn't plan that, but nevertheless, I can change that manually so you can get an idea of the alternative options for doing it interactively or for doing this manually. Accept the table. And now I have 7 lines between the 8 different degrees of freedom. Save this one. And then I can move forwards to the channel setup. That's the bare minimum you need to do in the geometry setup. Here you can see my acquisition system with 8 input channels on the front end that I've mentioned previously. I have to select one reference. In this case, I have the automatic impact hammer connected to channel 1. The type of transducer in there is a vibration transducer, and I can define some of these other parameters. In particular, I need to define it as ICPE, or integrated electronics, piezoelectric. Of course, it's a force transducer, it's measuring force, so I should also define this. And the actual sensitivity I can define as 22 millivolts per Newton. That's in fact, it's 2 millivolts per Newton nominal sensitivity for this particular force transducer. I have a couple of accelerometers connected here, and those have been provided with a power supply externally, so they're producing a voltage in AC mode, and so I'll give those a sensitivity of 200 millivolts per G. We could use the calibration workbook, which sits next to this one, to get proper or better actual sensitivity values than those nominal sensitivity values that I've entered for these 2 transducers. But in the case of modal analysis, these shapes are all relative, so it's not so important, not so critical to get those values absolutely perfect. The nominal sensitivities will be close enough. What I must do is define the point and the direction. I mentioned previously that it's important that the FRFs are labeled properly with respect to the geometry. Here I can choose to use the geometry to partially define my channels. In here I can refresh this table. There's my geometry that was created previously. I already told you that I have 1 sensor, and it's important to be able to understand which of the 2 sensors it is that's connected to the towers at that tower 1 level. So I can either follow the cable from transducer to my acquisition system, or I can also go to the impact scope quickly. And if I tap the top of the transducer, should be able to tell which one is on which channel. So that's the top one mounted at channel 7. And here you can see that the level is much higher on the channel 2. So in the channel setup, I've got them in the right order. So channel 1 here can be copied onto channel 2. So I insert that. Channel 7 here can be inserted onto channel 3, and it doesn't look like much has changed because we're not looking at the important parts of the table. But what's happened that is important is that these points have been redefined with the names. I will start my impact measurements from tower 1, and I will work my way up with my impact hammer all the way up to tower 8. That's a roving impact acquisition. So I'm similarly going to select tower 1 and insert that over this channel here. So both of these 2 are named channel 1. One of them is my accelerometer that's going to remain fixed at that location. The other one is my impact hammer, which is going to rove up the tower. I've defined Z in the upwards direction, which makes sense. I should also define the positive X direction. So you might imagine that since I'm impacting from this side of the tower, we'll call the direction of excitation minus X. To be honest, it doesn't really make too much difference. But it is important that my accelerometers, which are mounted on the back side and are measuring in the negative X direction, I'm measuring are both given the same direction if they're both mounted on that side of the tower. So because I'm exciting in this direction, that's a positive X impact and a negative X acceleration measured on the backside of this tower here. As I say, it doesn't really matter too much in the end because these shapes are vibrating from either side of an equilibrium position in the end when we complete the modal analysis. So that's my channel setup complete. I should save this project at this point. As I said, I'm skipping the impact, the calibration setup and going directly to the impact scope. Here now I can specify the ranges that I'm using. Remember the 3 R's of data acquisition: range, resolution, and rate. Ranging is the first one. We need to set our ranges to be appropriate for typical impacts. So I'm now impacting the tower at the top with the impact hammer and giving it an impact that is about the level of impact that I'm normally going to be using during the campaign. So I do a few impacts. The acquisition system is observing all the time. I set the ranges. Those green bars are indicating a good measurement is being made. I'm using most of the ADC to collect those measurements. And if I have a look at the force reference, you can see that it's using the maximum input range, 10 volts. We've got quite a good level of impact for that particular transducer. Similarly with the X direction measurements, that measurement at tower 7 is a little bit lower than the measurement at channel 1. We can change these subsequently during the acquisition campaign, but for now those will be good enough. So all of my channels are connected. I've got measurements. There's no problems with the grounding, or I haven't properly specified the signal conditioning. I'm getting good quality data from these example impacts. Now I have to really think about setting up the impact measurement campaign itself. So here I go into the triggering. This is going to make sure that when I strike the tower, the triggering is collecting the signals from just prior to the tower being struck, and for a period of time long enough to allow the response mostly to decay to 0. I'm going to deliberately choose to strike the tower at the top, and in this case I just want to do one impact. I made a mistake and didn't start the scope. So now we're measuring between impacts. I'm going to put my hands on the tower to remove any residual vibration and remove them gently so as not to pluck the tower into vibration. One impact, and there you can see a very nice, clean, sharp impact. As a result of that impact, the acquisition system is suggesting that we set a trigger level of 187 millivolts, as opposed to what's currently set. This is the default that comes out of the box, and an input range of 3.16 in this case. So it's suggesting to just change the input range down slightly, even though we've just set the ranges. And a pre-trigger of 0.037 seconds, 0.0037 seconds, so that we capture all of the impact. So I should apply those suggested settings, and then I can verify the trigger settings here. So again, hands on the tower to stop it vibrating, strike the tower. And there you can see now hardware triggered force signal down here. I'm collecting the full impact duration. If I zoom in on this axis by double clicking the number here, it's actually selecting the curve. There we go. Make this 0.01 seconds. There you can see now my impact, which starts from 0, rises up to a maximum and back to 0. So I'm collecting, this is all important stuff. I need to collect all of this as well as just the peak. And that's what the pre-trigger does. So I'm happy with that. We can move forwards to set now the bandwidth. The bandwidth is the range in frequency over which I'm doing my measurements. I'll check the bandwidth, then stop the tower, do another impact. Here you can see the characteristic force spectrum that I get with that kind of a short duration impulse. My useful frequency range is approximately 1 decade down from the peak. So if we look around about here, this is 3.2 kilohertz. I've got a useful frequency range of at least up to a kilohertz, perhaps a little bit more. And here you can see immediately power spectral density for the tower response. There are some good looking peaks within there, which is what I would expect for this kind of a multi-degree of freedom system. My next impulse of measurement will do a similar measurement, but looking at 4 times bandwidth. And now with 4 times bandwidth, we can see these characteristic, if you like, bounces in frequency domain. We don't have enough. We never expected to have enough to excite the structure at these higher frequency ranges. We're not interested in the tower beyond these first few hundred hertz here in any case. So this tip stiffness that we've used gives us a clean impulse, and we're happy with that. In fact, what we really probably would like to do in this case, because we're only interested in this frequency range here, is probably change this to around about a kilohertz. And of course, we can also change the spectral lines to give ourselves a bit more resolution in our frequency spectrum. If I go to the all settings, I get to have a look at the control of everything. So I'll just double this one. This is going to give me a 2-second acquisition time because I've now changed to half hertz resolution. So the bandwidth is fixed. That's the frequency range I'm interested in. I'm looking to just control the acquisition time. It's a lightly damped structure, so I want to use 2 seconds to give it a chance for the vibration response to decay. That leads to a half hertz resolution. This means that I can differentiate peaks that are quite close together in frequency. I'll keep those settings. Here you can see those are captured down here. And I can move to the next worksheet, the windowing workbook. There's a lot of curves in here now, but it's a similar process. I'm going to start the measurements. Now I'm deciding whether or not I need to apply any force exponential or force windows to these data to be able to improve the way that they lead to frequency response function. So here you can see my unwindowed reference measurement, my unwindowed response measurement. This is a multiple sine wave decaying exponential function that we can see here, and it doesn't quite decay to zero. Remember, I mentioned that this was quite a lightly damped structure, so there is still some vibration at the end of here, and it would be useful for us to apply, therefore, a force exponential window to try to force this to zero by the end of the block length, so that we satisfy the requirements of the Fourier analysis. So this reference here has been suggested to have a cutoff of 100% at 0.76. We can apply that suggested window, and you can see there now is the green window. So this was unwindowed, and now this will be the result after windowing. There's no real need to apply a force window, but it does apply a small one here. It notices that we can cut off effectively the measurement after this initial impulse, and that gives us a very nice looking force frequency spectrum. So those are good looking healthy signals that we have here. And of course, I'm experienced in this, so I know that you're less experienced. But if you see something that doesn't look good like this, then it's probably going to be the case that you don't get good measurements. We can ignore the driving points tab for this particular scenario. This allows us to choose which of the degrees of freedom we should do the excitation at. Effectively, it allows us to select where we should place the accelerometers that I've already placed at levels 1 and 7. So save the project. I can move forward to the measure sheet. So everything's now ready to do an impact measurement. So now I can define, okay, where am I going to do my measurements? How many averages should I increment? After each, I can choose to increment or decrement. There's lots of capability in here to implicitly or explicitly accept. Because I'm practiced at this, I'll allow it to implicitly accept. That means that if I do a dodgy impact, if I make a mess of my impact, I have to hit undo to remove it. Normally, it will just add it to the averages. So we start measuring. I'm now striking the tower at level 1. You can see the trigger was overcome and it's done the first measurement here. To begin with, I have impulse, response, frequency domain for both. Okay, this is a linear scale rather than a log scale. We can change that. Now you can see it on log scale, but this is what's important, my instantaneous FRF and my averaged FRF and the coherence function, which for the time being with only one average doesn't have any values in it. It only gets values when I've done more than one average. What I'm looking for is for the instantaneous FRF not to be too different from one impact to the next, such that the averaged FRF essentially just removes any noise. In the measurement here, you can see peaks for the various degrees of freedom and phase transitions through those resonances and the occasional anti-resonance also. So I'll do another impact. We'll get a second average. And now I've got nice coherence. Some little problems with my coherence just at lower frequencies, which we might be concerned about, but these peaks in the spectrum looking pretty good here. One more impact. It's always difficult at the lowest tower story to get really good coherence. This might lead to some challenges. So here you can see I've got my hammer. I will strike the structure at the level 1. I get some audio feedback. I get some nice looking FRFs. I'm going to do the second average, but between averages, I'll make sure that there's no residual vibration. Do another strike. And my instantaneous FRF should look the same each time. My averaged FRF should be essentially the same, but with the noise slowly being reduced. Any noise, low level noise in the average FRF should be reduced. After 3 averages, that's now complete. Good coherence. But as we move up the tower, so I can again restart that, I'm going to increment the point at which I'm doing the impact from. So I'm now at point 2, so restart the measurement. I'm moving to the second degree of freedom. I'll do my first impact. Happy with the way that looks. To the second one. Again, I still get some relatively low coherence. There's a particular drop around that anti-resonance here. Big anti-resonance here and the resulting low coherence. This is really more a problem with the instrumentation. It's never easy to get this very low frequency. Now moving up to level 2. 1. And it's important when I'm striking that I'm tapping the tower gently and I'm getting a clean, sharp impact. I'm tapping the tower in the X direction and at the same location on that degree of freedom. If any movement, change in direction, then obviously I get a different FRF each time. My averaging won't be particularly good. In this case, my coherence is not quite as good as it was for the previous FRF. It's not too bad. There's a few drops in the coherence, particularly around the anti-resonances, which I'm not too worried about. I'm more worried where I've got poor coherence at a resonance, particularly this low frequency here. It's quite challenging to get good coherence around that first and second low resonant frequencies, and that will be evident also in our mode shape, modal analysis, our processing subsequently. The shapes will be noisy. So just working my way up. Levels all the way up the tower, giving it time for the 2 seconds for the vibration to, and then I get that audio feedback. Can increment and start keeping an eye on that this name here of that the FRF is going to be labelled with is consistent with where I'm actually striking the tower. If I strike the tower at a different location to that which I've told the software I'm collecting an FRF for, clearly when I do the modal analysis I have a problem because it's going to be animating a different part of the geometry with data from somewhere else, and we don't want that. Now at level 5, And I'm just doing 3 averages, which is pretty much the bare minimum. I don't see much improvement after 3 averages. I might want to convince myself that I don't get any better FRFs for doing 5 averages. As you can see, with a bit of experience, it's quite a quick experimental measurement campaign to collect all of these data. Remember that it doesn't matter exactly how hard I hit the tower, because for a linear system, if I strike the tower harder or less hard, I'll get more or less response proportionally. I do try to keep the impact level reasonably consistent, not least because I've set the ranges on the acquisition system. I don't want to go giving it a huge impact and overloading my acquisition system. My green indicators here, if they go to red during the measurement, then I've overloaded the acquisition system and I'll be clipping the signal. And we would need to, that's exactly what I did there. Deliberately, you can see the orange light here, it went red. The software's intelligent, it tells me that I didn't do a good job of that. So I'm now at the top of the tower, and I can do my last 3 averages. It's my first measurement, very nice looking FRF. Second impact, great coherence, really happy with that. As I mentioned before, it does get easier the further away we get from the boundary condition, fixed boundary condition. That's my third impact. Beautiful coherence all the way, pretty much along here, except where I've got some anti-resonances and a very nice looking average FRF. So I'll save those data. There are some more functionalities in here, including the validation sheet, so I can confirm, for example, I've made measurements at every location on the tower. So if I select this channel, you can see my response measurement points. I can change the matrix presentation, and I can see for each of those 2 accelerometer locations, I've got FRFs because I've done measurements at each of the towers with my impact hammer. So I've got a data set that's fully populated. There are 16 FRFs in total, and it's these FRFs that I will use to produce my modal analysis. I can potentially do some post-processing. That's an optional workbook. If we've got good quality data, we don't need to do any post-processing. If I go to the modal data selection workbook, we're now here picking up where we started from with previous exercise, including the plexiglass plate modal analysis that we looked at in one of the lab sessions. I get this warning, there are too many inputs or more inputs than outputs. You might want to switch the FRF table. Yeah, indeed, we do want to switch it so that it's organized in this way. And if I select either one of these FRFs or the entire table and choose to show them on the geometry, we have a similar functionality to that which we had in the validate work before. The validate is part of the impact measurement acquisition workbook. The modal data selection and time MDOF and so on is part of modal analysis. So there is some duplicated functionality, but that allows us to be able to validate our FRF set when we come into modal analysis rather than when we finish modal acquisition or impact. I can choose to show the sum of the FRFs, and I can show the selected FRFs in the table as well. I can select one or more of those. And as you can see, if I've done a good measurement, then of course all my peaks should line up with one another. And all of the FRFs should have similar resonance characteristics. If I double click on this one, I can zoom in, say, for example, to 600 Hertz, and then I will be able to see that I've got peaks. And add a single cursor and make that cursor snap to values, and I can drag that cursor around and I can identify the frequencies of these peaks. If I put a cursor legend on, right clicking, then you can see the frequency of the first degree of freedom. First resonant frequency, I should say, is 4.5 Hertz, and these are the values for all of those measurements. In fact, I just really should look at those with the SumFRF. So if I select that one, I can move backwards and forwards using the cursors. That's the peak, 4 Hertz for the first peak, 25.5 Hertz for the second peak, 70.5 Hertz for the third resonant frequency, and so on. So the first thing to do with these data, 131.5 Hertz, etc. The first thing I can do with these FRFs, with this FRF data, is compare the frequencies with those that I've predicted from my simulation. But I want to do more than that. I want to animate these mode shapes. So I'm going to go forward to time multi-degree of freedom. And here I now have a stabilization diagram. I'll have a look at the SumFRF. I'll take just some subset of the available FRFs to me. I'll right click on this axis and change the format to log. And I need to importantly now choose the bandwidth over which I'm going to do the analysis. So similarly as to before, I'll change this frequency range to 600. That's going to allow me to get the first, I'll do it down about 2 Hertz, and I'm going to do an analysis of 1, 2, 3, 4, 5, 6, 7, 8 resonant frequencies. So something within this range. There are some of the resonances here, as you can see, as a result of the rectangular cross-section. We'll probably only look at the first few mode shapes. In fact, I might just, for the purposes of this demonstration, choose my bandwidth here to look at these first 5 resonant frequencies. Again, working along the mini workbooks here, you'll notice I have a mode indicator function here. I've got 2 responses, so 2 mode indicator functions. At each of these modes, potential modes, the mode, one or the other of the mode indicator functions drops to a small value. Moving forwards in the stabilization diagram, again, just having a look, probably changing to a log scale, and looking at these potential poles and picking one that's a vector in that case. As we remember, there was poor coherence here, so this is not the best. This will have quite high noise relative to the signal, so that's a bit of a difficult one to make that measurement at, just because it's such a low frequency. Other frequencies, I can see there's some very nice stable poles here. Potentially, I've got this one splitting a little bit. It's potentially a couple of frequencies competing with one another. Similarly here, I've got a little bit of splitting happening. Different FRFs have potentially different peaks, and that's why I get these 2 kind of columns of potential poles. Maybe I could have done my measurement campaign better. Let's move forwards and have a look at those shapes from those 5 candidate peaks that I've picked, and we'll just do a calculation immediately and have a look at those in the display. So there's a frequency that looks like the first bending mode for a cantilever beam. So I'm reasonably happy, but as I mentioned, you can see it's not a very clear, clean mode shape. There's a little bit of noise in there. And yeah, so perhaps I could have done a better job of collecting those measurement data. I can scroll forwards to the second mode, and there's still quite some noise on that end. That shouldn't look at all like that. My third shape, however, looks pretty good. I've got good measurement data at this particular tower. I can turn on the underformed tower. Similarly, I can have a look at the underformed nodes. So that's my reference. I can also use a quad geometry if I want to see it in 3 different degrees of freedom. but then I lose my annotations, and there are various other annotations that I can turn on. Let's have a look at the fourth mode shape. Importantly, now you can see these crossings of the zero axis, and that's characteristic. Increasing spatial density for higher frequency shapes. 2, 3, 4 locations along the tower where I don't have any motion for each of those shapes. I can proceed forwards and do other things like modification prediction. And have a look at making changes to the modal model rather than physically to the tower itself. Now I have to scroll all the way along here to find my modification prediction. I can choose, for example, to add a mass modification at this location of this amount of mass. See, it puts a blob of mass here and it lists it in the table. I can edit that one. I can add a spring damper, I can add a tuned absorber at different tower levels and so on to try to change the way that my structure responds, predict how I can change its characteristics, and then I can go back and try to achieve those physically to the prototype. Lots of things to explore. This is just an example, it's a quick run through how to set up a measurement campaign, build a geometry, use the geometry to define the channels, use the impact scope to collect measurement data, use the impact setup to define the triggering, the bandwidth, and the windowing, use the measure sheet to collect my FRF set, have a look at those FRFs, select them for modal analysis, and go ahead and complete the modal analysis through to producing frequencies and shapes in this table here.